the first presentation from Yogesh Wadadekar, who will tell us about the Indian participation in software and data processing based work packages. So Yogesh, over to you.
Yes. Thank you very much, Yashwant. The way I'm going to organize my talk is that in this first session, over the next half an hour or so, I'm going to tell you about what are the areas in software and data processing that we are going to participate in. We meaning the Indian team is going to be participating in over the next 6 or 7 years. I will not get into the specifics of resourcing and contracting and the processes behind development of the software in this talk. There's going to be a separate presentation in the afternoon where we will go into all of those details. My talk will be followed by another talk by Prabhu, who's going to tell us about Indian participation in hardware related activities. So mine is going to focus only on software and data processing, and Prabhu will cover the hardware aspects. So let's get started. So the SKA software is basically partitioned into two large areas. The total software budget is about 100 million euros, which is a pretty substantial amount of money. The money is partitioned into two major chunks. The first one is what is called science, data handling and processing, and that has a budget of about 55 million euros. The task of SDHP is to develop software for processing the very voluminous science data stream that is coming out of the correlator. As well as we shall see in the minute, the volumes of data that come out of the correlator are so large that it is not possible for us to adopt a traditional model wherein the data are simply stored and then analyzed at a later date. Because the data volumes coming out of the correlator are so humongous, there is simply no way that we can process those data at a later stage. It has to be done quasi real time so that the process data, which is usually much smaller than the raw data, can then be stored and distributed to the SKA regional centers, which I'll describe in a minute. Within the SDHP, the Indian participation is currently quite limited. It is limited to the Pulsar Search sub-element. At the end of my talk, I will say a little bit more about what that entails. But the bulk of my talk will be focused on the second major area of software development within the SKA, which is observatory management and control. And that has a budget that's comparable to SDHP. It's about 45 million euros. And the task of this OMC software is to orchestrate the entire observation, right from preparing the schedule for the observation until the observation is finally completed and the data are handed over to the SDHP for further processing. It is considerably more than a traditional monitoring and control system, since it includes various user interfaces for various stakeholders like astronomers, telescope operators, maintenance engineers, and the like. It also includes local interfaces to MNC systems of individual hardware items. Okay, so for example, individual hardware item may be a motor, which comes with its own monitoring and control system, but the OMC will have a well-defined interface to the monitoring and control system of that local device so that it can send commands to those devices and also receive monitoring signals from those devices and then take appropriate decisions. So all of this is within the scope of the OMC. To place this in the context of the total SKA cost, so this was a slide that was shown yesterday by both Phil and Joe, and you can see that the revised cost of building the whole telescope and operating it over the next decade, 2021 to 2030, works out to nearly 2,000 million euros, or 2 billion euros. That number 1986 that you see at your bottom left of the screen is the total cost of building the observatory and also for running it. The observatory budget is split into sort of two large chunks. One is the construction budget and one is the operations budget. Okay. The construction budget is about 2/3 and the operations budget is about 1/3. The last entry there for the observatory development program, 40 million euros, is just for development of new technologies, prototyping of new developments that has been reserved for. It's a relatively small amount for new developments. So as you can see, although the software budget of 100 million euros sounds large, in the context of building the whole observatory, it is not such a large amount. What are we building? We are building something known as the Observatory Monitoring and Control. Until recently, this whole system was known as Telescope Manager, the system that manages the entire telescope. So in this slide, you can see that this is truly the nervous system of the SKA, and therefore it needs to talk to various components of the telescope. Okay. So for example, it will need to talk to the infrastructure, because if the power goes down, the network goes down or something like that, then it is the telescope manager that will have the responsibility of communicating with the infrastructure and deciding what action to take. It has to provide user interfaces for observations to the operators and also to the scientists, because the scientists are the people who have the high level view of the observation. They need to see what a different set of data than what the operator sees, who's doing the low level execution of the observation. It may also need to talk with the central signal processor, which is spewing out data, which is then used by the science data processing system. It will need to talk to the signal and data transport system. It will need to manage it remotely. It will need to diagnose problems. It will need to transfer, make sure that the timing, these are the clocks at various places in the telescope, are all synchronized. And this is a very important thing in radio astronomy. So overall, telescope manager sits at the center of things. So although it is, one can think of it as just a monitoring and control system, because of this large number of very complex and complicated interfaces that it has with almost every other part of the system, that is what makes it quite tricky to implement. The telescope manager will also play an important role during commissioning, because unlike an optical telescope, which all gets built once and turned on once you have the instruments in place, in the case of a radio telescope, it always gets built out in stages. The moment you have a few dishes or a few aperture array stations, you can start collecting data. You can start diagnosing problems and so on. So in order to do that, one needs a working observatory monitoring and control system, which will allow you to do this job of commissioning, testing, and so on. And therefore, it's important that we develop a system that is perhaps not completely feature ready, but already usable within a few years. So here is a slide which shows the observation workflow of the telescope. So on top left, you have the principal investigator, the PI, who writes in a proposal. Then the proposal gets reviewed by external referees. And once the proposal is accepted, goes into the observation planning stage, where an operations planner looks at the requirements of that particular observation and see how it fits into the overall schedule. Then the scheduling is done, which is known as, which is in the form of what is known as a scheduling block. A scheduling block is basically a program that tells the telescope to execute an observation, right? It may be just be a script or something more complicated. Once the observation is scheduled, the scheduling block is run on the telescope and the observation gets executed. And during the scheduling stage and the observation stage and the actual low-level telescope monitoring and control system, the telescope operator will play an important role. During the observation scheduling, there is a arrow in red which says TOO events. These are target of opportunity events. These are special events, maybe a gamma ray burst went off or a supernova went off and so on, which you want to be observed immediately. And then that can feed into the observation scheduling and may require some changes in the scheduling blocks that have been prepared. Once the observation goes for execution, the actual execution is carried out by the telescope monitoring and control system, okay, and which may run its own script. So the scheduling block gives a high-level script of what the configuration of the telescope should be, what observations are to be run for what duration, and so on. The telescope management is the low-level counterpart of this, which actually sends signals maybe to dishes to point in a particular direction towards a particular radio source and then start observing and so on while continuously tracking the source. All of this functionality is included in the purview of the observation management and control. So when we develop the OMC software, we have to develop software that does all of these things. So to summarize, what will the OMC software do? First of all, it will accept science proposals, design observations, schedule them, and prepare the system for executing the observations. And then comes the step of the actual execution. It will orchestrate the hardware and software systems to control the observations through well-defined interfaces, which I just mentioned. It will also provide logging and alarm management and handle faults. Okay, so if something goes wrong, then it is the job of the OMC software or the telescope manager to take steps to rectify the problem. The problem may be reported from its own monitoring points, but it can also come through external interfaces. So for example, if there is a thunderstorm that is developing, there may be an alert that comes in from a weather station to the telescope. Then depending on the severity of the threat, the OMC software has to then decide what to do and take action accordingly. There is a lot of operational support data. So it will maintain the telescope systems through continuous logging of parameters to monitor the telescope health, and which I just mentioned. And these data can be very useful for performing diagnostics, particularly when combined with archive data. So all the engineering metadata that is generated within the telescope manager will be preserved in an archive database, so that if a problem occurs, then it can be quickly diagnosed based on previous such observations which are sitting in the engineering metadata database. All of this data there will be large volumes of data, and you want a good user interface to the data that different people need. And as I mentioned previously, operators, maintenance engineers, scientists, etc., all need to look at the same data from different views. Okay, so one will have to develop custom user interfaces that will allow each of these stakeholders to access the data that they need. We will also have to have some kind of drill down, because often you just need a overall dashboard which gives you a summary of what's going on. And if something goes wrong, then you need to have the ability to drill down, go deeper, and search exactly where the problem is occurring, and then you can come up with a solution. So the SKA has decided to adopt something known as the Tango controls framework to implement this functionality. So what is Tango? Tango is an open source software architecture which was initially designed to control particle accelerators by the particle physics community. And it has a large library of modules that are relatively easily adapted to the needs of the SKA. So every software module which is directly involved with the management of the telescope will be built on top of this common framework. So this decision was taken about 2 or 3 years ago. It is now frozen. So there is no option to Tango. One has to use Tango for any software module that directly interfaces to telescope operations. Okay. So Tango has this concept of Tango devices, and there are interfaces that allow you to talk to Tango devices or to storage devices. So for example, here you can see there is a subsystem log storage, there is a subsystem archive, there is a telescope data archive, and so on. Then there is a Tango device that will allow you to connect to each of these archives and get a view. There are complex interconnections between all the Tango devices, the storage devices, and all the handlers and the various nodes that are there as part of the entire telescope operations. Let us now spend a few minutes looking at data flows in the science data processor. So the science data handling and processing receives two types of observational data. Now, this is not engineering data. This is the science data from the astronomical observations. So these are of two types. They could be visibility data, which are coming as outputs from the correlator, which will be received as a continuous flow, which has to be imaged. And there are also non-imaging data. This is a second class of observations where one is observing often, for example, time series data, where you're not correlating the data, but just storing it as a time series. And that gets buffered at various stages and often received as discrete chunks. Sometimes it is desirable to run the telescope in both imaging and non-imaging modes. And in that case, we call these commensal observations. There are two backends that are running at the same time, and the same data, the same observation may be processed as both imaging and non-imaging data. In addition to producing these science data products, the STP also computes the calibration data. It generates a lot of metadata. It generates alerts, and it maintains global and local sky models. And all of these will be exchanged with the OMC software. So the OMC will have an interface with the science data processing system to receive these monitoring data and also to send some data to the SDHP. So the SKA operations will be orchestrated by the Observatory Monitoring and Control System. It's a continuous operation 24/7. It includes data processing. It includes multi-queue observation scheduling to enable dynamic response to maximize output. By multi-queue, one means there is the standard queue that is produced by the observatory, and then that can be augmented by target of opportunity observations. The observations will be controlled by the SKA Observatory. The observers in general will not be physically present at the telescope. There will be some operators who will run the system, but the observers will be remote. And this system will have the capability to multiplex observing programs to take advantage of subarrays and commercial observing. What subarrays mean is you can partition the telescope into smaller groups. Okay, those are called subarrays. So let's say if you have 100 dishes, you can partition them into 5 groups of 20 dishes each, and then you can carry out a completely independent observing program, possibly even at a different frequency with the subarray. The last point here is something that I mentioned previously, that a practical implication from the size of the telescopes and the breadth of the science is that the flow of raw data from the outputs from the correlators and the beamformers will be too large to store in any foreseeable storage system. Okay, we are talking of many terabytes of data getting produced per second. We are talking of something like, even after processing, we are talking of order of half a exabyte to an exabyte of processed data that needs to be stored and distributed. Because of these large volumes coming out of the correlators, significant science data processing will need to be done in quasi-real time. What is quasi-real time? Need not be done immediately. Maybe we'll have storage buffers to store about, say, 8 hours of data, but nothing more. So we have to get going and process data at the same speed at which it comes in. The buffer is only for emergencies. If something goes wrong and you need to buffer the data for a few hours, that will be possible. Observers will receive data products such as images and pulsar detections, which require much less storage. So this is the decimation idea, wherein the raw data are very large, but by the time it goes to the scientist, you have decimated it significantly. And the users will access their data primarily through the SKA regional centers. In the afternoon, we have another talk where we will describe how the regional centers will operate. So this slide tells you about how the SDHP processes the data, okay, and its connection to the Observatory Monitoring and Control System, and also to the SKA regional centers. So the data flows from the central signal processing unit in the form of visibilities, pulsar candidates, etc. It gets ingested into the science data processor, and then gets processed through different pipelines. Okay, there may be a standard visibility pipeline or multiple visibility pipelines. Similarly, the time domain data may have its different pipelines depending exactly on the kind of data that are being processed. Once the data are processed, they go into an archive, a science archive, which goes into some long-term archive as well. Once the data sits in the archive, then it goes into the delivery system, which then transfers the data possibly to a mirror archive, and also to one or several of what are called SRCs, SKA regional centers. The observation, monitoring, and control system interfaces with the science data processor, okay, by talking directly to the local monitoring and control system of the SDP, but also by providing metadata for the observations which are required for the processing. So for example, if a certain dish has gone down during an observation, then it is the telescope management or the OMC that knows about it. Is going to have to transfer that information to the science data processor, so that that part of the data, which is clearly bad, it's a device that's not working, can be ignored during the processing. This is a very trivial example, but there are many more complex use cases that correspond to this, that require this kind of information exchange. A bit about availability. We get asked this question a lot from the software engineers. So in the case of the SKA, the engineering analysis indicates that the telescope design that has been made should offer an inherent availability of greater than 95%. Okay. What does that mean? From the perspective of observatory operation, we are more interested in a number called the operational availability. It's the relevant figure of merit. Both the telescopes, both SKA low and SKA mid, are required to have an operational ability of at least 95%. What that means is that it can perform observations, including signal processing and data reduction, with at least 95% of its collecting area, and including associated signal and data processing resources. This level of availability is quite acceptable because in aperture synthesis telescopes, the loss of a few antennas, front ends, or even segments of a signal path only degrade the performance slightly, and we are able to live with it. We don't need very high availability. We don't need 99.99% availability. There is flexible scheduling, the possibility of forming subarrays, which also provide an effective mitigation strategy to prevent such kind of failures, which will inevitably occur, from adversely affecting a scientific project. What that means is that if part of your array goes down, you just reconfigure it quickly into a subarray so that it doesn't infect or affect in the rest of the system, and you continue with the observations with the other available systems. And then later on, once this thing comes on, it can be plugged in once again into the main telescope. While building the hardware and while building the software, there is a conscious attempt to build in redundancy at all the critical failure points. As far as possible, items have been designed as line replaceable units, where you can just simply go and pull something out and push something in, and you're done. This is very important because remember, these telescopes are located at very remote sites. Just getting to the telescope can be a difficult exercise. Particularly if the weather is bad, it can be quite difficult. So it's quite important to design hardware and software to be redundant and failure resistant.
So, Yogesh, just
Yeah,
to interrupt, just keeping track of time, folding in
yeah.
that we started a bit late. You have about 5 minutes or a bit less
Yes,
remaining.
I'll be done in actually 2 or 3 minutes. Yeah,
Okay.
yeah. So, I have spent quite a bit of time describing the observation and monitoring and control and its connection to the science data processing. I'll spend this last slide talking about Pulsar Search with the SK. So we have uh, uh, a very small participation in this Pulsar Search activity, which is basically what happens is that you want to search for new pulsars, and this is a very difficult exercise primarily because there is the parameter space that needs to be searched for is very large. Okay, you know there's a pulsar, but don't know how far it is, and you don't know what its dispersion measure is. You don't know whether it's a short period pulsar or a long period pulsar. You don't know whether the pulse is narrow or whether it's wide. You don't know if the pulsar is in a binary orbit. If the pulsar is in a binary orbit, then there can be changes in its period with time. And pulsar observations are also strongly affected by radio frequency interference. Uh, because of all these constraints, one needs a fairly sophisticated algorithm for searching for pulsars, but one also needs a lot of compute resources in order to sort of sample this parameter space and observe the pulsar. Now, this whole pulsar search will be done both with SKA1 mid and SKA1 low. Both of these telescopes have the ability to produce multiple beams. What this means is that you can simultaneously observe different parts of the sky at one go, and therefore cover a much larger area of the sky than you otherwise would. And one is talking of very large operations per second. So there's a number here. The Pulsar Search has about 10 peta operations per second, and it's going to generate about 60 petabytes per day, right? So it's truly a huge challenge. Uh, our contribution in this effort is listed on the right hand side, the contribution areas. Uh, so this, of course, will require extensive GPUs and FPGAs and things like that. Uh, and we are going to contribute a member to a much larger team, which is working on the Pulsar Search sub-element of the SKA. But we budgeted for that, and we'll be providing a developer for about 7 years for the entire construction duration of the telescope. So I'm going to end here with a note that I've just given you the sort of background that we will need for the short session in the afternoon, where we will talk more about the logistics of the teams. How many teams do we need? How are they to be organized? What part of the OMC software they will develop? How much time will we have? How much money will we have to deliver this, and so on? And how are we going to work together with teams in other countries? Remember, this is an international effort, even for the OMC. The OMC is not going to be built entirely by India, although we have roughly a 50% contribution to the total effort. But we have several other countries who will be our partners. So I'll describe all of that in the afternoon session. This session was merely to give you a background on the OMC software. So if there are any questions or comments, I'm happy to take them.
Okay, thanks, Yogesh. That was a quite clear, detailed presentation. And let me just see if there are any questions. So those who are in the Zoom, please raise your hands or type it in the chat box if you have a question. And if there are questions on the YouTube stream, then we can take those also.
There is one question in the YouTube.
Yeah.
Yogesh.
So I see that it says that if SK availability is greater than 95%, then telescope maintenance will be in 95% or in 5% of that time.
Yes. So, so one will not be able to have the sort of follow the traditional maintenance model that we have in some of the existing generation telescopes. wherein we simply take a chunk of time, say once a week or once a month, to do the maintenance. What one we may have to do here is minimize that kind of maintenance by really going for very high quality hardware and software, and also designing it in such a way that it can be replaced. Hardware components can be replaced as line replaceable units, wherein you don't have to take everything down. We'll also have to make everything very modular so that you can switch off only a very small part of the system where the problem exists, and uh, uh, and then solve that problem. Which means that the observatory management control should have the ability to provide drill down to the line replacement unit level. Okay, so the OMC should be able to say that, okay, this particular card on this device at this location has failed. So then the engineer's job should be as simple as driving to the location, identifying the part that has to be replaced, pulling it out and pushing in the new part and restarting the system. So this is going to require a paradigm change. SK is going to require a paradigm change on the part of astronomers on how they do astronomy, but it will also require, for success, a paradigm change from engineers on how they do the diagnostics and how they do the maintenance.
Yeah, okay. So that was a question from the YouTube channel by Jayant Kumbar. There is one more from the YouTube channel by Kiran Mehta, who asks, why does Pulsar Search require real-time computing, and what kind of compute operations constitute it?
The first part is relatively easy to answer. Why does it require real time? Because remember, we are exploring a very large parameter space, and that is generating very large volumes of data. So once you start generating 60 petabytes a day, unless you look for the pulsar, find it, and otherwise throw away the data, unless you actually do that, you will not be able to store that data. So 60 petabytes a day in 10 days will become 600 petabytes. In a month will become an exabyte. Okay. We don't have that much storage. So that's the reason why we need to do this very, very rapidly in quasi real time, if not real time. What are the exact steps in a Pulsar search operation? I'll defer this question to either Yashwant or Prabhu, whoever wants to take it.
Yeah, I can give a quick answer to that, to Kiran Mehta and others, that the Pulsar search operation normally for any single stream of data requires you to first de-disperse the data for a range of trial dispersion measures, because the dispersion measure is unknown, and the data is taken in multiple frequency channels across the band, and then search each of these de-dispersed time series for the presence of periodic signals, which is done by can be done by two different methods. One is to take a Fourier transform the power spectrum of the signal, and then look for harmonically related peaks in the spectrum, or just do a folding of the data for different trial periods of the pulsar to see if a signal shows up. There are additional complications, that if you are looking for a binary pulsars in binary systems, then you need to worry about the fact that the period of the pulsar may have changed appreciably during the duration of the observation. Then you have to apply additional signal processing methods to try and compensate for that. So that adds one more parameter to the already two-dimensional parameter search, and so all that in the case of the SKA, it's further complicated, because often you will be doing this on multiple beams of data coming in simultaneously, from especially for an instrument like the SKA low, and then you will be having parallel such pulsar search processes running on different directions of the sky that the telescope is able to look at simultaneously. So that all adds to the total amount of complication. Yogesh, there's one question from Debangana, which says that is the telescope manager centralized or is it distributed with master-slave architecture?
Uh, so the answer to that, of course, is that it's a combination of both. Okay, it is. There will be a central node. Okay, but that will talk to LMCs, small node LMCs, sub node LMCs that are distributed. So there will be a centralized LMC, OMC running in the main control building, but there will also be distributed OMC instances that will be running in a hierarchical fashion further down. But there aren't too many layers there. Eventually, you will reach a local device, okay, which might be a servo motor, for example, and there you will need to talk to the LMC of that, and that will be quite decentralized, that process.
Okay.
One more question I saw about from Kiran Mehta, which was there's no mention about electromagnetic follow-up of gravitational wave candidates. Is the SKA not suited for it? So the quick answer is no, it is definitely well suited, and the gravitational wave candidate would be one of the streams that are coming in as target of opportunity. So if a gravitational wave detection happens, then it can immediately be used to trigger a target of opportunity event on the SK. And definitely the EM follow-up or radio follow-up of gravitational wave candidates is one of the science drivers of the SK.
Okay, then there is a question from Kiran Narkhede asking pulsar data processing will be at the observatory DC or at RDC. I guess RDC is regional data center and observatory DC is probably the observatory data center.
Yes, so it will be at the observatory. It's not going to happen at the regional data center. There is no possibility of moving so much data upstream. In fact, it will probably happen at the observatory or close to the engineering data center. I'm not sure. Or maybe it will happen, but it will certainly is a responsibility of the observatory. It will not be happening in the regional data centers.
Right. Okay. This probably maybe the last question, which is not directly related to your talk. There's a question from Rohit Wadadekar asking how many subarrays can GMRT have, and maybe I can just quickly answer that. The GMRT design provides for up to 6 subarrays. And we often have observations using 4 subarrays. Not often, sometimes have observations using 4 subarrays for specific purposes. So that is a feature that's available in the GMRT also. Okay, I think we've exhausted most of the question and we have also exhausted the time. So thank you once again, Yogesh, and then we will move on.